to Lab 5. In this lab, we are going to be doing more plotting, specifically with univariate data, which is really all we've used so far. That just means one variable. And so when you're looking at one variable, all you can really do is look at its distribution. How is that data distributed? Because that tells you a lot about what you can do with it and, what the population may look like. So the HTML file is on Blackboard. You also need to make sure that you downloaded the datasets folder that I made available for the last lab, because you will need one of the datasets in there for this lab. So you want to start by creating a new R script, last name underscore lab 5. You do want to make sure and open RStudio with your R project folder. So again, here is my workspace right here, Geography 316 for this class. And so you want to open the R project. I think we did that on the first day. So what happens when you open it, RStudio with your R project, is it makes sure that you are in the working directory that you need to be in. So you can see here this file path. This is going to be my working directory, and that's exactly where you want to be, because this is where all your labs are. And so now you can create that new script. Go ahead and save it. All right, and we are off. So let's go back here. All right, so once again, we are going to be using ggplot, which is probably what we'll use for most of the rest of the semester. There are other ways to make plots in R, but it's my opinion and the opinion of many others that ggplot is the best, both in terms of being easy to use and easy to understand, as well as producing high quality graphics. And of course, I know that easy to use and easy to understand are relative terms, but hopefully by going through it step by step, you will start to understand the basics of how that grammar of graphics is built, so that when you see ggplot code, you can read it, or when there's something that you want to create, you'll have some idea of how to do it. 1 second. There we go. All right. So first things first is you need to load the tidyverse. ggplot is a package that is part of the tidyverse, so you could also load it by itself. But a lot of the functions that we're going to do to get our data in order so that we can make sense of it are also part of the tidyverse. So it's easiest just to load the tidyverse. And so because you're going to use that in your script, you need to make sure that that's the first line. Anytime you open a new R session, only base R is loaded. So any packages that you use in your script need to be loaded before you can run your script. So it's always a good idea to put them as the first line of your script. Unless actually probably what is better is a comment as your first line saying, this is my lab 5. All right, so we will load the tidyverse. So shortcut there, again, you can run here, or if just whatever line of code you're on, you can hit Command Return for a Mac, or I believe Control Enter on Windows, and it will run that line of code. And so of course that means it gets sent to the console, and you can see here that the tidyverse has been attached. All right, so first we need to generate some data. And so we've seen these functions before. We've seen the setSeed function also. Again, it's not strictly necessary, but if we all set this same seed, we will all get exactly the same numbers in these data sets. even though there are 1,000 values in each of these data sets, we will all have exactly the same numbers. And so that helps me if you're having problems, if we all set the same seed. So I would discourage you from copying and pasting like this because it really does help to get in the habit of typing these things out. It really helps you learn. I have already typed them out because I put together this document and I don't think I should have to do it again. So I am taking the shortcut. Of course, I'm never going to know, but again, it's really going to help you if you type this in yourself. And so you can see up here in our environment that these variables are being created. These are vectors, numeric vectors, as you can see by these square brackets, 1 to 1,000 of all of these values. Oh, sorry, so we have our normal distribution, which this says that we want to take 1,000 draws from a theoretical normal distribution that is defined by a mean of 100 and a standard deviation of 20. This says we want to draw 1,000 times from a uniform distribution. So a uniform distribution is governed by the minimum and maximum values. So here we have a minimum of 0 and a maximum of 20. And so every value in between 0 and 200 has an equal probability of being randomly selected in this draw. So then we also have the exponential. So exponential is a J-shaped distribution. It kind of, oops, sorry. How do I get that to go? There we go. Is a J-shaped distribution, kind of like, this is going to be like that, but I guess, anyways, it's a J-shaped distribution. And so it's governed by this rate, which is the speed of the decline of the distribution. All right, so we have, oh, didn't run that. So again, you want to set that seed every time before you do one of these random draws. So now we have our 3 variables here. All right, so before we are able to use them in ggplot, we need to make them into data frames. And so there are different ways to do that. I think in lab 3, we used the data frame function. There is also a function in the tidyverse called tibble. Does the same thing. I think it was last lab, lab 4, that I talked about tibbles a little bit. They're just a special kind of data frame that behave nicely. And one of those things being they print nicely in the console, only the first 10 rows by default. So that's what we're going to use here. And again, you can't, to use ggplot, it has to be a data frame. It can't be these vectors here. If we tried to give one of these variables to ggplot, it wouldn't know what to do with it. So here, we are going to redefine our variables as data frames. So a couple things. What we're doing here is we're saying we're going to create a tibble called dat.norm. We want the column to be called obs for observations, and we want that column to equal this vector of data. Because if you'll recall, every column in a data frame is a vector because it can only have one data type per column. And so notice also that we are using an existing variable at the same time that we are redefining it. You can very easily do that. So do be careful because you can easily overwrite variables that you didn't mean to. But in this case, that's exactly what we want to do because we no longer need this dat.norm because we only need the dat.norm that's going to be a data frame. So we will run all of this. So now you can see how these changed in the environment. Now you can see that there's one variable, so that means one column, 1,000 rows. So instead of being a vector that's just, a series of values, now we have it where it's like a spreadsheet. All right. Okay, so now we are getting back to ggplot. This is the basic grammar of ggplot. You open your ggplot. All right, so you open your ggplot like this, and then you tell ggplot what data you want to use. So in this case, let's say data equals dat norm, right? And so hopefully you figured out that this auto-populate is very helpful. As something comes up, you can navigate here with your arrow keys and then just hit enter when you have what you need. That can also be very helpful to avoid typos. All right, so we have our data there, and now we add to it. We add to it a geometry because we need to tell ggplot what sort of geometry we want. Do we want a histogram? Do we want a bar chart? Do we want a dot plot? Do we want a scatter plot? There are lots of different geometries, and we will get to more of them later. But here we're going to focus on histograms again. So we will add on our histogram. And now we need to give it the aesthetic mapping. So we're saying, okay, here's our data. It's dat.norm. We want you to make a histogram with it. But now we need to tell ggplot which one of the variables in our data frame we want it to map to the histogram. So in the case of a histogram, you only have x values. You don't have x and y values. So in this case, we actually only have one variable in our data frame, but that doesn't really matter. We still need to tell ggplot which one. And so that is our observations. And so I think I have you guys writing these full specifications here like this. I think that it's very helpful, especially as you're getting started, because it makes your code more readable. And it also helps you remember what these different pieces are. So we can run it like this. And that looks goofy because my window is smushed. But so there is the histogram. You could also run it just like this. You don't need these words before the parameters, the arguments that you're putting in. Those are the names of the arguments. And like I said, they really help me when I'm writing code to keep track of what I'm doing. Because especially when you're getting started, you might see this and not really understand what that means. Of course, it gives us the same plot. But this makes it just a bit easier. You can say, oh, okay, dat.norm, this is the data that's being plotted. Okay, observation, that's the aesthetic that's being mapped to the histogram. So I would encourage you to keep writing code like this, especially just as we're getting started. I also wanted to point out that I think in the last lab, this aesthetic mapping here, in this one, we have it down here in the geometry. I'm pretty sure last lab we had it up here with the data. And so you can do it either way. It doesn't matter for us right now. This is saying when it's up here with the data in the ggplot that every single geometry, every specification that you put into the ggplot is going to use this data and this variable. When you write it like this, it's saying, okay, ggplot, everything that you do in this plot is going to be using this data. But right now, only the histogram is using this aesthetic. So you could actually add on additional geometries, which we'll do later, based on different variables. So that's the only difference. But right now, they both work. And so like I say, this plot, I don't know, it looks okay. But I don't know, it's kind of boring. It's not going to catch many eyes, especially if you are trying to bring attention to something in a report that you're doing. So there are lots of ways that we can gussy it up. Also, you probably noticed this error message here. The default for histogram and ggplot is to use 30 bins no matter what. Most of the time, almost all of the time, you want to adjust that because like we saw in the last lab, I think, maybe the one before, you can't always see the whole picture just based on the default. So you can add that here, just a comma after this mapping argument, and say bins equals, let's try 50. And so that is what our histogram looks like with 50. This is what it looked like with 30. Let's try 100. So you can see that it's maintaining the same basic shape, but the more that we add, the more jagged it gets. Let's do 1,000 because we have 1,000 values of our variable. And that gets almost unreadable, right? I mean, it looks kind of cool, but it doesn't really tell us a lot about the data. Let's go small. So these three, the 30, the 50, and the 100, I feel like have the same basic shape. The 100, maybe not so good. But, once you get to the 10, maybe you're starting to lose something. So I would say for this data set, 20 probably looks pretty good because we do want a generalization of the distribution. Otherwise, we would just plot every single point. We don't want so few bins that it obscures variation in the data. We saw that last time with the bimodal distribution, but we also don't want so many that we're not able to generalize about the data. And it's really just kind of a heuristic thing. You will get a sense for it, but it's always a good idea to try out a couple different numbers of bins. You can also specify instead the bin width. And so in this case, you can see our values are pretty much from 50 to 150. So let's try a bin width of 10. And so you can see that looks about the same. The smaller the bin width, the greater the number of bins you're going to have. And so again, you'll just kind of get a feel for that as you make more of these. So here I have a series of code chunks for you. And so these are just some of the customizations that you can add to a ggplot. These are all going to be histograms right now. I want you to run all of them and then tell me, and so I have each of them lettered. For this question number 1 here, I want you to tell me which part of the code is kind of adding something new or changing from the basic histogram, which is this one here. So what part of the code is changing it and what does it do? And so I kind of gave you a freebie here. I told you that this one, in the first instance, if you run this code, it changes the outline of our histogram bars red. And so what you would tell me in your answer is that this part of the code here, this color equals red in the geometry, changes the color of the bin outlines. And so I want you to run all of these and tell me what they do. And so here, like I said, you are able to add multiple geometries to the same ggplot. So copy this out. So here we have a slightly different geometry. This is a density plot. So a density plot is kind of like a histogram, but instead of having those bins, it's showing more of a theoretical distribution because it's just going to be a line. And so even though we don't have like an infinite continuous amount of data points to really be able to have a line, it approximates that for us. And so here, instead of putting anything in the ggplot, I'm adding both the data and the mapping to the geometry because each one of these is different. If each one of those different distributions that we created, if those were all in one data frame together, we could specify that here. But because we have 3 data frames, that means we have 3 data sources. So for this geometry, the data is our normal distribution, the mapping is the observation, and then I have the color here. This geometry is our uniform distribution with a different color. Then our exponential, oops, sorry, my cat is sleeping behind the computer, with a different color. So we will be able to see them all on the same plot so that we can compare the distributions. So let's run this. We can zoom in here. So that's pretty neat, right? We have added all 3 of our distributions to the same plot, so you can really see the difference. So this blue is our normal distribution, the orange is the uniform distribution, and then the green is the exponential, with me trying to draw it in the air for you. And so here for question 2, I want you to describe to me the shapes of those distributions and how they're kind of different from each other. And notice here that this color is outside of this aesthetic mapping. If you include it in the aesthetic mapping, it will display in different colors by category. We don't have any categories right now in our data, but we will at the end of the lab. But I just wanted to point out here that this is outside. So we have one argument here, comma, one argument here, comma, and another argument here. All right. So then I go on to talk a little bit about outliers, which hopefully you've talked about in the lecture portion of the class. Outliers are data points that kind of exist outside of that generalized distribution. What is the general shape of the distribution? Outliers are far outside of that. Think about household income in the United States. A lot of people are kind of lower to middle class. You know, maybe people are making between $30,000 and $100,000 a year. And then there's Jeff Bezos, who makes about $320 million a day, right? No exaggeration. So that is what's known as an outlier. And the problem with outliers is that if you try to do something like take the average, get the average household income for the United States, if you add Jeff Bezos in there, that average number is going to be way higher than it should be. It is no longer representative of our data. So it can be good to kind of identify possible outliers in your data. And so there's not a hard and fast rule for determining what are outliers and what are not. And people also have different opinions on what to do about them, whether or not you would remove them from your data before you do any analysis. We're not going to get into that quite yet here. But I do say that one of the most commonly accepted definitions of an outlier is based on what is known as the interquartile range. So the median is your 50th percentile, right? So 50% of your data points are above the median, 50% are below. The 25th percentile and the 75th percentile are also what's known as the first and third quartiles. So 25% is your first quartile, 50% is your second quartile, 75% is your third quartile, and then 100% is your fourth quartile. And so the interquartile range is the difference between that 25% and 75%. So between your first and your third quartile. Hopefully that's not news to you guys. All right, so here it's very easy to calculate those. With the quantile function. So this function takes a vector. So here we've given it one column from our data frame, which again is a vector. And then you tell it what percentile that you want. And what it's going to do is give you the cutoff number in your data set such that 25% of the values are below it and 75% are above it. Here, for the upper quartile, this is saying, okay, of our observations, give me the numbers such that 75% of the values are below this number and 25% are above. So we are defining two variables here, our lower quartile and our upper quartile. And so you can see here, they've been added as values. It's a named number. So really that just means it's a variable that consists of one number, which is this 86.5 and 112. So we can also calculate the median. Just with this median function, we could have just as easily used quantile and written in 0.5. But what I want to do is add them to a ggplot, our histogram, so that you can get a better idea of what I'm talking about. All right. So here are our quartiles. So this red line is our median, so the 50th percentile, 0.5 quartile. And so you can easily see that approximately half of the data is on the left, approximately half of the data is on the right. Because remember, this is the count of the observations that fall into each bin. So here, maybe it looks like one or two observations have these low values. Maybe one or two have these high values. But in the middle here, this is what? Over 100 of our values fit into this middle bin. And of course, that's the primary characteristic of a normal distribution. That's why it has this shape. So this yellow here on the left is the 25th percentile, which is that 0.25 quartile, which is the lower quartile. All right, so here you have about 25% of the data, and then on this side is about 75% of the data. All right, so now to calculate the interquartile range, we could easily just subtract the upper quartile, or subtract the lower quartile from the upper quartile. So here's our answer, 25.78. There's also this handy function, and you notice I didn't save that to a variable, so it doesn't show up here. I've only sent it to my console. There's also the IQR, which calculates it for us. So this, we give the whole vector that we need it for, so our observations. So we want the IQR of the observations from our dat.norm. Oops. And you can see they're the same number. All right, so now what we want to do is create a new variable that represents the 1.5 times the interquartile range. So for lack of a better idea, we'll call that I. Run that. And so now what we need to do, because it's an outlier is defined as something that lies, okay, so below the lower quartile by the IQR times 1.5%, or above the upper quartile by the IQR times 1.5%. So what we want to do is subtract this value I from our lower quartile, and we want to add it to the upper quartile. And those numbers will be our cutoff values for what we might potentially consider to be outliers. So let's plot this again. But instead of our 25th and 75th percentiles here, we're going to plot these lower and upper bounds. And so I guess I forgot to say again, what I'm doing here is I'm making a ggplot with this normal data. I'm making a histogram with this variable, the observations, and we've picked a bin width of 5. And here what I'm doing is adding a different kind of geometry, which is a vertical line. So here you can see these are just vertical lines. And these vertical lines are defined by their x-intercept. So this value here on your x-axis, this number line, the x-intercept is this value, right? So here, our x-intercept is equal to this lower bound, and here the x-intercept is equal to this upper bound. And so here is our normally distributed data with those upper and lower bounds. Again, 1.5 times the interquartile range, above or below the first and third quartiles. And so you tell me, I don't know, do we have outliers? That's question number 3. I'm not going to answer it for you. So tell me, does it seem like we have some outliers? And in general, why can they be a problem? And so now we're going to move on to dot plots. This is just another kind of geometry, same as the histogram or the V-line or the density or the frequency polygon that you did earlier. I haven't done here, but is in the lab earlier. And so a dot plot is not that different from a histogram. It shows the data kind of the same way, except you can see that instead of a single bar, we have these dots. And each dot represents one value. So we have 1,000 values here. We have every single one of our values. So you can better see how many values fit in each bin. You can see this is 1, 1, 4. There's 1 here, 3, 4. And that's just potentially a bit easier than this, where we think maybe that's 1, but we don't know. So again, pretty much the same, telling us the same thing about the data, but maybe a little bit easier to see the exact numbers. And so here, hopefully it doesn't get too tricky for you, but we want to be able to make this same plot, but with the dots that may be outliers colored differently. And so we have to manipulate our data frame a little bit in order to do that. And so I'm introducing here 2 new functions. One, and they're both part of the tidyverse. I think dplyr is the actual package, but again, we loaded the entire tidyverse, so we have access to them. This mutate function here, what mutate does is it adds a new column to your data frame. Case when allows the value of that new column to be based on one of the existing columns in your data frame. So we'll get more into it here. I'm also introducing this funny looking symbol that's a percent and then greater than and then percent. It's what's known as a pipe, and there are pipes in many programming languages. The primary thing it does is it allows the output of a function to be piped directly into a new function without having to create an intermediary variable. So let's see if we can help that make sense. So here, I will show you about mutate. So what this is saying, this pipe here, is it's saying take this dat.norm and pipe it into this mutate function where we're creating a new column called new column where every row is going to have the same value of 1. So let's run that. We're not saving it as a variable, but remember, because it's a tibble, it prints out nicely like this. It's just easy to read. So here is what we created. So we have mutated the original data frame, meaning we added a new column. We've changed the original data frame, but it's still the same data frame. So now we have our observations. We also have our new column, which we called new column, where every row has this value of 1. All right, hopefully that kind of makes sense. Because we could have also written it without the pipe, like this. So this is saying, okay, we want to mutate this dat.norm, create a new column equal to 1. And so hopefully you can see that this first argument that the mutate function takes, we've just moved outside of the function and added this pipe. So this pipe is taking this dat.norm and it's making it the first argument in the mutate function. This does the same thing. But when you write it like this, to me, it's a bit easier to read, especially when in some of these functions you start having a lot of arguments, and so this line might go on for a while. You can easily see what you're acting on, what you're doing something to. And it also means that, like I said, you can, and there are keyboard shortcuts for all of these things, just so you guys know. There's a keyboard shortcut for this little funny arrow. There's a keyboard shortcut for this. If you're interested, I'll try and post something on Blackboard, but just do a Google search for RStudio Shortcuts Windows or RStudio Shortcut Macs. It makes it a bit easier when you start writing like this. So now, let's create another column equal to 2. Let's see what happens there. So you can see that we have that other column here. What we didn't have to do is say something like, okay, this mutate, we'll say that was named X, and now we want to redefine X as mutate X, another call equals 2. So let's look at X. So you can see it's the same, but here, well, let's do this so you can really see. Again, exactly the same. But here, we didn't have to create any intermediary variables. You see here, we had to create 2 variables, even though what we're doing is just renaming this, overwriting it. We didn't have to create more than one variable. We were able to say, okay, take that norm, pipe it into mutate, take the output of this, which is still our data frame with the new column, pipe it into this, and here is our output. So hopefully that makes sense. Maybe it doesn't, I don't know. One neat thing is you can also do it like this. Just put a comma here. So you can have you can add more than one new column within a mutate function. So exactly the same again. We just had one column here, they're separated by a comma. All right, so now let's talk about case when. So here, we just specified a single value. All of the rows, they're gonna have the same value. But maybe very often that's not exactly what you wanna do. You wanna say, okay, I want all of the observations with the observation value is less than 90. I want them to have one value in this new column. All of the values that are more than 90, I want them to have a different value in that column. So that's when case when comes into play. So again, we've got our dat norm. We are piping it in to the mutate function. We are creating a new column, so just the same as here, we say mutate new column, except instead of just having a single value, now we have this case when function. So here we're saying, when the case is that the value of the observation is greater than 90, I want that value to be a y. So that's a character value, it's in quotes. We could also put a number that wouldn't be in quotes. But here, since it's a categorical variable, we're creating two categories. A character is a good choice. And so this little tilde, is just saying, okay, this is the case, and then separated by the tilde, this is the value when this is the case. And so then you can see here, when the case is that the observation is less than or equal to 90, we want to give that value an n. And so you can see it here. We have our new column, mutate new column. That's what it's called. And so now all of the values here that are greater than 90 got a y value in the new column. All of the values here in the observation column that are less than or equal to 90 got an n in the new column. I think that's pretty neat how easy that is. So hopefully that makes sense. And I have all of that in here too, so you'll be able to reference this. So let's do something a little bit more complicated. I promise this is the end of the complicated stuff for this lab. All right, let's go over this. So dat norm, we are doing something to it. Oops. So we want to save it as a variable. We're going to do something to it and save it as the same variable, just like we did earlier, because we're adding new columns. We don't need the variable that doesn't have those columns. We just want it with the new columns. And so saving that, we're saving it with the same variable name. So we're saving our variable dat.norm. What that variable is going to be equal to is dat.norm piped into mutate. So again, we're taking dat.norm, adding new columns. That's what mutate does. We are going to call that column outlier. All right, so again, the name is here on the left and don't need to put it in quotes. Outlier equals case when. Okay, so what are our cases? And there are two new symbols here too. So when the observation value is greater than the upper limit, so it was that IQR times 1.5 plus the upper quartile that we calculated earlier. So if the observation is above that upper bound, or, which is this vertical line, or the observation is below the lower bound, we want to give it a Y. So Y being yes, this could potentially be an outlier. And then we have the comma. So we have our second case. The second case is when the observation is less than or equal to the upper bound, and the observation is greater than or equal to the lower bound. We want to give it a no. That value we would not consider to be an outlier. So these, you can see there are two criteria for each. This is an or, this is an and. And so this and is saying, okay, here's the lower bound, here's the upper bound, anything in the middle, so it's both above this bound and below this bound. And the first case is saying anything that's below the lower bound or above the upper bound may be an outlier. So let's run that. And so you can see now what it looks like. We have our observation column, and we have this outlier column. See, most of them aren't, but, well, I don't want to keep scrolling there, but you can always, and it gets a little wonky when you have really big data frames, you can sort with these. So there, you can see our Y's. Most of them are N's, some of them are Y's. That's the nature of outliers. And so now what you'll be able to do, and why I pointed this out earlier, is use that to change those rows, those observations with the Y values, make them a different color. All right, so ggplot, dat norm. Hopefully that looks normal to you right now. Should have written it like this, sorry. Data equals dot norm plus this dot plot, geometry dot plot, our mapping, aesthetic mapping. We're showing the observations. But see now this fill is inside this aesthetic mapping. That means we're also mapping the fill, which is a color, the inside color. We're mapping that fill to a column, which is our outlier column. Let's see what that looks like. And there you go. Isn't that neat? So it automatically creates a legend for us here. You can see there are different colors because this fill is part of the aesthetic mapping. If we took it out, and put it here, it doesn't work, right? It doesn't know what to do with this outlier, because it's a variable. And that needs to be inside this aesthetics. And if we gave it a color, it changes the color of all the points. Well, you can see it there. You can see it there. It changed the color of all the points. So, again, what this is doing is it's mapping it to something that you see here. So it's mapping the fill of the points to this outlier variable, which is that column that we created. And then this just takes you through how to save plots. It's very easy. What I want you to do is in your workspace, create a new folder. I've already done it, called plots. So here we've got, some of this you won't have, data sets, plots, and your scripts, right? So create that plots. And this is important because what we're going to do, and because we're in this R project, it knows exactly where we are, we can just say gg save, and this operates on the last plot that you made. So if you want to save multiple plots, you need to run this gg save function after each one. And then you just give it the path. So here we want it to be plots. And a fun tip is if you open your quotes and then press tab, it pops up with everything that is in that folder. You can also then type the P, and so now it's only the things with P's. We want this plots. So here we're going to save it in the plots folder, and now we need to give it a name. And so, you know, whatever you want to name it that makes sense to you. Maybe I specified what you should name it. Probably something with your last name. So when you turn it in, don't have any problems. Let's say so Wesley dot plot. And then you give it a file extension. So here, a PNG, which is just a type of image file. We could also save it as a JPEG. We could save it as a PDF. And then you just run that. And so you can see here that it's saved. And what it's doing is saving it there we go, in the dimensions of this graphics window here. So you may just want to resize it until it's about how you would like, and then run your code. Also down here on the console, you can just press the up arrow and it will cycle through what you've run. So here, just one up, it'll run the same thing that I just ran. And so this should overwrite that file that I just saved. And so now you can see the dimensions are different. You can also, so see, that's a much better, those are much better dimensions. You can also specify in this ggsave function, so we'll add a comma here because we have a new argument. Let's say our width equals 5. Let's say we want it to be square. And the height equals 5. And then you need to tell it the units that you mean. So are we talking 5 centimeters or 5 inches? And we'll say inches, which needs to be in quotes. So we have our path, the width, the height, and the units. Oh, come on. And so now we have our square plot. All right, so hopefully you all will enjoy learning how to do some new cool things in this lab. So like I said, there are the 3 questions embedded kind of in the lab notes. They're numbered and they're in bold, so answer all of those and then go through and answer these. So like I said, you're going to need to read in data that's in your data sets folder, make some histograms, make a histogram with at least 3 of the customizations that I go over earlier in the lab, and then save it. You're going to upload it along with your script. Then I want you to talk about the distribution of those temperatures in the data sets. And then I want you to go through what we just did, creating a column that indicates whether or not an observation might be an outlier, and then create a dot plot showing which of those observations might be outliers. All right, thanks a lot. Bye.